is Afolabi, and we are here for another physics class. In the previous classes, we have started with refraction of light, and I've introduced you to what refraction is about, and it is all about what? Changes in wave speed when wave moves from one medium to another. If you have not watched that video, please try to watch that video once again before we move on to the next aspect of refraction of light. Today, we'll be looking at refraction of light through triangular glass prism. In our previous videos, we have checked refraction of light through rectangular glass prism and also through materials using real depth and apparent depth. So today we are moving on to rectangular glass prism. Let's say we are giving a rectangular glass prism ABC, okay? And the angle of incidence, of the light, this is the incidence radiation. What we have here is the incidence light, okay? With angle of incidence I through the normal is refracted. This is the refracted light. Okay, you can see the angle of refraction, small letter r, and this is the emergence on the other side. So, as light is moving from air, okay, into the glass and back to air, you can see that the speed of the light is changing. As it moves from air to glass, it moves closer to the normal. Don't forget, anytime light moves from a less dense medium to a dense medium, the speed will reduce such that the light will now move closer to the normal. That is what happened here. And when it got back into air from a dense medium to a less dense medium, it moved further away from the normal. So anytime light is traveling from a dense medium to a less dense medium, what happens? It moves further away from the normal, okay? And when it is traveling from a less dense medium to a dense medium, it moves closer to the normal. Now, for a prism such as this, you can see that the refractive index of the material can be obtained as well as the sine of the A plus dm over A over 2. Now, what the A stands for is the angle of the prism. The angle of the prism. If the prism is equilateral triangle, then the angle will definitely be what? Will be 60 degrees. So your A is the angle of prism, which is usually 60. A is usually 60 degrees for equilateral prism. Okay, the angles will all be the same. Now, what is dm? My dm is known as the minimum deviation. Dm is minimum deviation. Now, when a graph of I is plotted against dm, okay, what's my d? My d is the angle between the line of incidence and the line of emergence. Look at, this is the line of incidence, this is the line of emergence. When you trace both of them in here, the angle formed between the line of incidence and the line of emergence is the d, which is known as the deviation. Now, if I should plot the graph of the deviation against the incidence, I will get a curve, which is this way. I'll get a curve, which is this way, okay? Now, the minimum point of the curve is where my minimum deviation is. Minimum point of the curve is where the minimum deviation is. And that only occurs when your I is equal to E. So you could be asked that where do you get a minimum deviation of your triangular glass prism? You only get a minimum deviation when the angle of incidence is equal to the angle of emergence. That's number one. Or rather, the curve of your D against I is at minimum point. So the value of the dm and the value of the angle of the prism can be used to calculate the refractive index of the material. Of course, my A, mathematically, my A is 2r. My A is 2r. What does that mean? You know this equation is actually synonymous with the one of Snell's law. The one I gave you earlier on Snell's law, which says that the refractive index is what? Sine I over sine r. So my A is 2r, and my dm is 2 into I minus r. Okay? We can do a check-in by putting these two equations into what we have here. So I can put my A and dm into what I have here. So I'll plug A and dm in the refractive index. What do you get? Refractive index becomes sine. What's the value of A? The value of A is what? 2r. Okay? Plus, what's the value of dm? The value of dm is what? 2i plus 2 minus 2r. Okay? Divided by 2 over sine A over 2. What's sine A over 2? Sine A over 2, that's sine 2r over 2. Okay? So following the mathematics up, you can see that your 2r cancels this 2r, and my refractive index will become what? Sine 2i over 2 over sine 2r over 2. So this 2 cancels out this. And what do we have? We have sine I over sine r over sine r. So my refractive index is sine r over sine r. And this is the Snell's law, remember? This is the Snell's law which I gave you earlier on. So the Snell's law is still being represented by the equation which we have here. It's nothing different. So don't think when we have this equation, then we are not stating the Snell's law. It's still the same thing as the Snell's law, okay? It's just that this time, we take cognizance of what? The angle of the prism and what? The minimum deviation of the angle of incidence and the angle of emergence. So once you know the angle of incidence and the angle of emergence, you can find the refractive index of the material. Let's try a question out. Question: find the refractive index. We have to find the refractive index of a glass prism where the angle is 60 degrees. That's the angle of the prism, and we have the minimum deviation as 30 degrees. So let's have the solution. We have the angle of the prism to go 60 degrees. That's the angle of the prism. Okay. Then the minimum deviation dm is what? 30 degrees. So we can use that to find the refractive index, which is sine what? A plus dm over 2 divided by sine what? A over 2. So slotting the value of A and BM, we have sine, what's A? A we have 60 plus 30 over 2 over sine, what's A there? A is 60 over 2. So what do we have? We have refractive index to be sine 90 over 2. So the refractive index of the glass, of course, you substitute that's 30 plus 60 divided by 2, that gives you 45. Then 60 over 2, that gives you 30. So sine 45 over sine 30, that's what? 1.41. And that's the refractive index of the material. Refraction is the concept of total internal reflection. Total internal reflection. A very, very vital aspect of refraction of light. And what do we mean by total internal reflection? It is a condition you find out when light is traveling from a dense medium such as glass to a less dense medium like air. Normally, we expect refraction to occur when light is traveling from one medium to another. But in total internal reflection, refraction does not occur. Now, what are the causes of this refraction not occurring? And we have reflection back into the medium. In total internal reflection, what actually happens is that we don't have refraction of the light, we have reflection back into the medium. And this only occurs when light is traveling from a dense medium to a less dense medium. Actually, when we have light traveling from a dense medium to a less dense medium, as you increase the angle of incidence, the angle of refraction will also be increasing. Let's say we have initial angle of refraction here. It will be increasing as you are increasing this. It will be increasing to this place, until it will have refraction around here. So refraction increases this way as incidence is increasing. So as the angle of incidence of the light radiation in the dense medium is increasing, the angle of refraction in the less dense medium is also increasing. And as the angle of less dense medium, as the angle in the less dense medium is increasing, the reflection will start showing little by little. That is, initially you have a light reflection. Later you have a very strong reflection. When you have that very strong reflection, we call that condition total internal reflection. So we have two conditions for total internal reflection. The condition is that one, light must be traveling, light must travel from dense to less dense medium. Then secondly, the angle of incidence must be greater than a certain angle we call the critical angle. Angle of incidence must be greater than the critical angle. Critical angle, small letter C. Conditions for total internal reflection. So for you to have total internal reflection, these two conditions must be met. For total internal reflection, as I told you initially, you don't have any form of refraction. Normally, when light is traveling from one medium to another, we are supposed to experience refraction in the new medium. But what we see here is that we have a strong reflection of the light back into the initial medium. So we can simply define our total internal reflection as a condition, okay, when light traveling from one medium to another medium does not refract. Don't forget, the light does not refract, but does what? Reflect back into the initial medium. So you have light traveling from one medium to another, no refraction here, but you have a reflection back into the initial medium. And that is the definition of the total internal reflection. But these are the two conditions for total internal reflection to occur. Number one, the light must be traveling from a dense medium to a less dense medium. Then secondly, the angle of incidence, as I showed you here, the angle of incidence must be greater than or equal to the critical angle C. So what is the critical angle C? Of course, the critical angle C is the minimum angle that is necessary to be overcome before total internal reflection will occur. Of course, you can calculate the critical angle by looking at the scenario we have here. Look at the scenario we have here. The refractive index of glass is sine I over sine R. But in this case, the light is traveling from glass to air. Remember, this is when the light is traveling from air to glass. So if the light is traveling from glass to air, then the refractive index will be the other way around. It's going to be from glass to air, and this will be sine R over sine I. So my sine R in this case, since there's no refraction, is what? 90 degrees, because you don't have any form of refraction. So we have sine 90 over what is the sine I in this case. For total internal reflection index of glass, which is a refractive index of glass, will be sine 90 is 1 over sine C. So how do we find the C? Sine C will be 1 over the refractive index, and C will give me the arc sine of 1 over the refractive index. So with this, you can find the critical angle of a glass medium. Whenever you have light moving from one medium to another, as a summary now, once the angle of incidence is more than the critical angle, the light will experience no refraction and you have a strong reflection. Okay? And that condition is known as the total internal reflection. Now, the value of the critical angle C can be calculated from what we have done here. As what? The arc sine of the refractive index. For example, calculate the critical angle. Calculate the critical angle of a glass medium of refractive index 1.41. So how do we do that? Very simple. The critical angle will simply be what? C equal to the arc sine of 1 over the refractive index. And that will be what? Arc sine of 1 over 1.4. And you can fill it up with your calculator. Of course, getting the value of C is very, very important, because above C, any angle of incidence that is above C will lead to what? Strong reflection back into the medium. And that is total internal reflection. Remember, you can always pause this video and rewatch this at any time. And don't forget to drop comments after the video. Thank you.